Okay, so let me get started on the last practice midterm of the class. So first one is state the definition of a Cauchy sequence xn. Okay, so this is a sequence which says for every epsilon greater than 0, there exists some n in the naturals so that the terms xn minus xm are less than epsilon for all n and m greater than or equal to n. Okay? So really this is just kind of put here so we can say the next step, which is to say the negation of this. Okay? So remember, for the negation, essentially the rule is that for all goes into there exists and vice versa. Okay? So what the negation of a sequence being Cauchy, I'm maybe I'll write it out. A sequence xn is not Cauchy if there exists an epsilon greater than 0, so that for all n and n in the naturals, there exists an n and an m greater than or equal to n, so that xn minus xm is greater than or equal to epsilon. Okay? All right, and finally, on this one we wanted to prove from the definition that 1 plus negative 1 over n is not Cauchy. Okay, so proof, again, since we're showing something is not Cauchy, we have to just show the existence of some epsilon. So we will say let epsilon be equal to a half. Okay, and then we have to show that for any n and n, so then for n in the naturals, we can choose, let's just say, for example, x sub n plus 2 minus x sub n plus 3 will be equal to 2, which is greater than epsilon, which was a half. So I guess I could have chosen epsilon to be 1 or 1.9, but any epsilon works. Okay? Oh, maybe I should say this is just, of course, equal to, well, it's either, 0 minus 2 or 2 minus 0, depending on the parity of n. Okay, whether it's even or odd. Okay, so part 2, you want to prove that the sum of two Cauchy sequences is Cauchy. Okay, so let's prove this. So we let xn and yn be Cauchy, and let epsilon greater than 0. Okay? So what we know that there exists, let's just say some n1 in n, so that xn minus xm is less than epsilon over 2 for nm greater than or equal to n1, since it's Cauchy, and there exists some n2 in the naturals, so that xn minus xm is less than epsilon over 2. Oh, sorry, that's... let me erase that. Sorry, that should be yn and ym. So yn minus ym less than epsilon over 2 for n m greater than or equal to n1. N2, sorry. Okay, so well, now we take the sequence, so for n and m greater than or equal to the max of n1 and n2, we know that the sequence xn plus yn minus xm plus ym, that's less than or equal to xn minus xm plus yn minus ym, that's less than or equal to epsilon over 2 plus, strictly less than epsilon over 2 plus epsilon over 2, so strictly less than epsilon. Okay, so let me go on to number 3. Okay. So this says we have x1 being equal to 3, and xn defined inductively as 2 plus 1 over xn minus 1, okay, for n greater than or equal to 2. Okay, so you want to prove that this is contracting. And then compute the limit. Okay, so let's take a look at the sequence, or the term, xn plus 1 minus xn, right? This is the thing that we need to compare to xn minus xn minus 1. Okay, so what we want to show, maybe we'll just put this here, you want to show this is less than c times this for all n and for some positive c between 0 and 1. Okay, so let's write out what this is. So this is 2 plus 1 over xn minus xn. And now the trick of these is that you somehow want to find xn minus 1 in there. Okay, so we have to introduce in xn minus 1. Okay, so I will do this by just writing this in terms of xn minus 1. Okay, so this is 2 plus 1 over xn minus 2 plus 1 over xn minus 1. And so the 2's cancel, so we just get 1 over xn minus 1 over xn minus 1. This is equal to xn minus 1 minus xn over xn minus 1. Okay, so this is good. This is where we've kind of gotten to the point where we can compare these. And of course what we want to do is say that these terms are, well, so I can write this absolute value as xn minus 1 minus xn over this product. And we want to say that this product is reasonably large so that we're dividing by a number smaller, or so that we end up multiplying by a number smaller than 1. So in this case, it's easy to see that xn, or I guess I'll write it this way, xn is greater than or equal to 2 for all n, right? So it gets a little tricky if you had a negative number, okay? But since you're starting with a positive number, well, it's easy to see that xn will always be positive, but you're also getting 2 plus some positive number. So therefore, it's certainly greater than or equal to 2, okay? So therefore, this product is greater than or equal to 4. So I can say that this is less than or equal to xn minus 1 minus xn over 4. Okay, and that shows it's contracting. with c equal to a fourth. Okay, and now this will be, well, to find the limit, we do a similar trick that we've kind of used before. The limit is going to satisfy L is 2 plus 1 over L. So we get L is equal to 2L plus 1 over L, L squared minus 2L minus 1 is equal to 0. So we end up with L being 2 plus or minus square root of 8 over 2, which is just 1 plus or minus the square root of 2. Okay, so let me go on to problem 4. Okay, so we had to find the accumulation points of a number of sets. Okay, there's no proof necessary, but I'll give at least some justification here. So the first set was the natural numbers. Okay, so I'll just use this to denote the accumulation points. The accumulation points, the naturals, is the empty set. Okay, so remember, if you're looking at an accumulation point, if you want to show something is an accumulation point of a set, then you would take a point x, and in any neighborhood, you would have to find a natural number. Okay, so this can only occur if you take your neighborhood small enough if x is honestly a natural number, so that every neighborhood that you have contains x. Okay, but remember, when you're taking an accumulation point, you're taking the interval x minus epsilon, x plus epsilon, minus the midpoint, and then intersect whatever set you have, right? This should not be empty for any epsilon. And so for the natural numbers, if you have any real number, it will either be a natural number, in which case you could just take epsilon to be a half, or it will be between two natural numbers, and then you just take, epsilon smaller than the distance between any of them, okay? Or between the two. All right, so for the next one, it was 0, 1, union 1, 2. So the accumulation point, let me call this S, the accumulation point in this case is just the closed interval 0 to 2, okay? So this is similar to something you saw in the homework where 0, 1 became 0, 1, 1, 2 would become 1, 2. Now in this case, you're missing the 1 from this, but this is kind of included in both of these accumulation points, right? So once you take the accumulation points, you pick up 1 from both of these sets, okay? And the proof is similar to what you would have seen on the homework, or what we saw, I think, in the lecture, okay? So again, the point is, if you take any neighborhood of 0 or any neighborhood around 2, it's going to intersect the set S. Same for any neighborhood around 1, and actually for any point between 0 and 2. Okay, so this one is also very similar to the accumulation point. Again, is just closed interval to 0, 1. Okay, so the point here is that this half, once you take accumulation points, you fill in. You fill in this missing value, because any neighborhood around a half is going to contain elements between 0 and 1. All right, and same thing for the endpoints; they get thrown in as well. Okay, so let me do part 5, which is we had a set S, or a subset of the real numbers, and then we took S bar to be S union the accumulation points of S, and then we had S double bar, okay, so that's just, well, it's S bar union the accumulation points of S bar. And what you have to do is show that these sets are equal. Okay? So let's see how you do this. So the first thing is that, well, certainly S bar is a subset of S double bar. Okay, so we really just have to show that any element here is an element in here. Okay, so we will show that S double bar is contained in S bar. Of course, this is, since this is S bar union something, this is the same as showing that the accumulation points of S bar are contained in S bar. So in other words, S bar is closed. Okay? Well, so we're going to take an X in the accumulation set of S bar. And actually what we will show is we will show that X is an accumulation point of S. Okay? And then we're done, since this is a subset of S bar. Okay, so how does this work? Well, you know that X is an accumulation point of S bar. So for any, maybe I'll say let epsilon greater than 0, since X is in the set of accumulation points of S bar, we have that X minus epsilon, X plus epsilon minus X intersect S bar is non-empty. Okay, so in other words, there's some S bar, an S bar in this intersection. Okay, and what we want to conclude, since we want to show that X is an accumulation point of S, well, we'd be happy if S bar was actually an element of S. Okay, so if S bar is in S, we're done. Okay, otherwise, well, it's in the accumulation set. Okay, so otherwise S bar is in the accumulation points. But that means that we can find a neighborhood, any neighborhood of S bar must contain further elements of S. Okay, so let me draw the picture here. We have X minus epsilon, X plus epsilon, and then we found an S bar, okay, in the accumulation, or in this neighborhood. If it's in S, we're done. Otherwise, if it's an accumulation point of S, you take a little neighborhood here, and it is going to be, you're going to find a new S in S. Okay? So either it's an element in S already, or since it's an accumulation point, you can find an element of S which is close enough to it that it's still contained in the X minus epsilon, X plus epsilon neighborhood. Okay, so I can say a little more carefully. So otherwise X bar is in here. So if we choose epsilon prime to be the minimum, well, of either X minus S bar, X plus epsilon minus S bar, or X minus epsilon minus S bar. I'm just cooking up a way so that no matter where S bar is, we're taking a neighborhood where the epsilon prime neighborhood is going to be contained in the X minus epsilon to X plus epsilon neighborhood. Okay. There will be an S in S bar minus epsilon prime S bar plus epsilon prime minus S bar, and that this S is an element of S, okay? And therefore, we're done. Okay, so this S shows that X is an accumulation point of the set S. Okay, so finally we had these two questions about series. Okay, so the first one was prove that the series sum from n equals 1 to infinity of 1 over n factorial is convergent. Okay, so to do this we're going to use comparison, okay, or the comparison test, okay. So what we know is that if we take the sum from n equals 1 to infinity of, be a little careful, 1 over 2 to the n minus 1, well, we know that this is convergent. Okay, and actually we can say this equals 2, okay? On the other hand, we have that n factorial is greater than or equal to 2 to the n minus 1 for all n, right? Because n factorial is, n times n minus 1 all the way down to 1. So maybe I'll write down to 2, okay? And this is greater than or equal to 2 times 2n minus 1 times, okay? So it's the same number of terms here, it's just these increase and these stay 2. Okay, so now therefore, since 1 over n factorial is less than or equal to 1 over 2 to the n minus 1, we get that the sum converges. Okay. You could also just use the fact that these are positive terms. So by monotone convergence theorem, you only have to show the series is bounded, and then again, it's essentially the same argument to show that, say, the series is bounded by 2. Okay. Okay, so finally in 7, our last one, we had to find the sum from n equals 1 to infinity of 2 times 1/3 to the 2n. Okay, so the point is that we always, when we're doing this, we have to kind of convert everything into something that we, a geometric series that we understand, okay? So in particular, this is equal to the sum, is equal to 2 times the sum from n equals 1 to infinity of 1/3 to the 2n, okay? You could wonder why I can take the 2 out, but so what I should really say is first this is convergent. Okay, and therefore we know that if you take the limit of like 2 times a sequence, then it's, it's 2 times the limit. Okay, so that's why you can do things like pull the 2 out of a series. Okay, so this is equal to 2 times the sum of 1/9 to the n. Okay, and then I want to replace this with n equals 0 because that gives me the formula that I like. So I say that this is 2 times 1/9 times the sum from n equals 0 to infinity of 1/9 to the n. So I get 2/9 times 1 minus, 1 over 1 minus 1/9. So I end up with 2/9 divide 2/9 divided by 9/8. So I get a quarter. Okay, so anytime you see a series that's kind of like this, in some sense, where you have something which looks like a geometric series, but the terms are not exactly in that form, you have to do some algebra to convert it into a geometric series, and then use the formula that we know. Okay. Okay, so that's it. Thanks. Good luck, and I'll see you on Wednesday.